The concept of superconductivity was born back in 1911, and with it, over time, fantasies about super-fast trains flying on magnetic cushions and life-saving medical scanners and, well, a lot more besides. One scientist working to make this fantasy a reality is Professor Elie Zeldof of the Weizmann Institute of Science.
Hi, David.
Professor. So, what puts the super in superconductivity?
Well, you have to keep in mind that any electrical wire, even the best one, has some finite resistivity. Namely, when you supply electrical current to the houses, you lose some energy on the way through the resistance in the wire. Superconductors are sort of materials which have absolutely zero resistivity. Namely, you can transmit electricity over vast distances with absolutely no resistance and no loss of energy. You can take a wire, make a loop of it, run a current in it, remove your battery, and the current will run forever.
It sounds like a dream. Will it come true?
There are a lot of dreams. Some of them are already becoming realities, some not yet. For example, levitating trains, namely trains on magnetic cushions that float above the rails and go at amazing speeds. With superconductors it's possible, but there is a limitation, and the limitation is temperature. This unique phenomenon of superconductivity occurs only at very low temperatures, up to 140 Kelvin, which is about minus 200 Fahrenheit.
Oh, that's very cold.
I can demonstrate you some superconductors in the lab.
Absolutely.
You're welcome. All right, so take this piece of magnet, and this is a superconductor here. It's cold.
Yes.
See how they react to each other. Yeah, try to force it in. It's pretty hard. So actually what you are doing, you are forcing magnetic field into the superconductor. It's pretty hard.
It is, yes. Looks as if it'll go on spinning forever.
Theoretically true, but in practice it works only at low temperatures. Once the temperature of the superconductor increases, this levitation and the spinning will stop. So now in order to understand what's happening, we want to be able to see the magnetic field.
Right.
So for this, we have developed a special technique which allows us actually to visualize directly the magnetic field that penetrates into a superconductor. Do you happen to have a credit card?
Well, I never leave home with that one.
All right. Very smart.
Gold cards, I couldn't know.
Right. What is important is this side. This is where the magnetic information is stored. And if we put it in our setup, take a look.
What am I looking at exactly?
Basically what you see is the straight lines, each representing 0 or 1.
Well, in my case, it must be zeros.
Well,
so this is what my overdraft looks like.
right. So we are visualizing here the magnetic field of the credit card. And actually, we're not interested in credit cards, we're interested in superconductors.
So what you're doing then is just basically being able to see what is invisible.
We are looking at the magnetic field that penetrates into the superconductor. When you were trying to force the magnet on top of the superconductor, the magnetic field penetrates into the material, into the superconductor, in the form of whirlpools. And what we have discovered with this setup is that they can form different phases, different states. For example, they can be in an ordered state, like atoms in a solid. On the other hand, when temperature raises, these vortices melt into a liquid phase. This is important for applications because once the whirlpools are in a liquid phase, the magnet that you saw falls down. So our research is to try to understand these vortices, their interactions, their behavior, in order to improve the performance of these materials. It's very emotional, very exciting, and when you get new results, you can't sleep at night. It's really fun.
This Weizmann Institute study should further our understanding of superconductor performance, bringing us one step closer to the as yet unreachable goal of a resistance-free electro world. And those hovering trains.